All right, 1, 2, 1, 2, 1, 2. All right. Hi, welcome to THERMO Boys. So today we're going to be dealing with a compressor problem that deals with air, and we're asked to find our actual work, our reversible work, and the mass flow rate of the water. Because in the problem here, the compressor is going to be cooled by the water, which will have a change in temperature of 10 degrees Celsius. So to first start off this problem, we have to analyze what we're given. You see that we have a volumetric flow rate here. So the first thing we're going to do is remind yourself that m dot equals v dot over little v. So that equals 4.5, and make sure you're in meters cubed per second over your specific volume. But you're like, how am I going to get the specific volume if I'm dealing with air? There's no tables that I can go to. Well, just write down your P, V equals RT equation, and you're given your pressure, your temperature, and the R value here, since we're dealing with air, is 0.287, so we can just solve for that. Times 293, and make sure your temperatures are in Kelvin. And then you'll see that your little v is going to be equal to 0.84091. And when you plug that back in here, your mass flow rate is going to be 5.35 kilograms per second. All right, that's just gonna help us start off the problem, okay? So now we're gonna write our Exergy balance equation, and that's gonna look like this. X in minus X out minus X destroyed equals the change in exergy of the system. All right, so this is really important that you start off every exergy problem with this. So since we're going to be looking for our reversible work first, we know that our exergy destroyed is going to be 0 because we're talking about an ideal situation. And we're going to assume that this is a steady state system, so this also goes to 0. And we're left with whatever goes in is going to equal whatever goes out. Well, let's analyze it. So what do we have going in? And since this is a compressor, we have work going in. So this xi will expand into work in, which in this case is the same thing as work reversible, minus or plus xi minus x out. And when we solve for this, we'll see that the work in equals x out minus x in, which is actually the same thing as saying x2 minus x1, because what goes out is at stage 2, and what goes in is at stage 1, all right? So this is how we're going to find the work reversible, by using this formula. And we're going to assume that in this case, our ambient conditions are going to be the same as the inlet conditions. So our exergy at stage 1 is a big old fat zero, all right? All right, so this leaves us with just the x2. So let's just write out the exergy equation with 2 and naught, because x naught is going to be the same thing as x1 since the ambient conditions are the same as the inlet. And the base equation is going to look like this. M dot, which is what we just found, times the change in enthalpy minus T naught, which is the ambient temperature, S2 minus S1. And then all that plus your change in kinetic energy that we will use because we were given initial and final velocities. All right? So that's your base equation for the exergy. So now we're just going to have to start plugging stuff in. And now you see that we're going to be seeing H's, but we're dealing with air. So the H's will turn into Cp T2 minus T1. And your S's, since we're dealing with air, will turn into Cp ln T2 over T1 minus R ln P2 over P1. And in this case, you can do the unit analysis yourself. I'm not going to do it here because it's going to take a really long time. But when you have all of this, this is going to be in watts. and you're gonna have to convert it into kilowatts because that's what we want our exergy in terms of. So instead of dividing it by 2, you're gonna divide it by 2,000, which is the same thing as saying 2 times 1,000, because since we have watts and we want in kilowatts, we just have to divide by 1,000. So that's exactly what we're doing here. So this term, the velocity term, is going to become plus 80 squared, because our V2, we were given that it was going to come out at 80 meters per second, so 80 squared minus 0 squared, because it came in ambient conditions, so it didn't have an initial velocity. So all this over 2,000, which will simplify, this term simplifies to 16 over 5. And so now we just have to start plugging in stuff into our equation. So what do we know about the CP? Well, if you look at your thermo tables, you'll see that CP for air is 1.005. And the temperature that it came out at, it doesn't matter if it's in Kelvin or Celsius, because we're just taking a difference. So this can be 60 minus 20. And for this, just get your values again from the tables, and you'll see that CP is 1.005 times natural log of T2 over T1. Now this is really important because we're dealing with air, you want it in Kelvin. So the T2 is going to become 333 degrees Kelvin, so let's just write that. And your T1, this becomes 293 Kelvin. So let's just go back to plugging in here. And then your R value, you can also get that from the tables. It's 0.287, and you'll have times natural log of the pressure ratio between in and out, which is just going to be 900 over 100. So now that we're done getting all these terms and just plugging in numbers, you have to be very careful when you plug it in your calculator. And let me make sure you guys know that this is 293. So once you plug in all of this into your calculator without making any mistakes, hopefully you'll get the same result that I did, noting that m dot we got was 5.35. So your exergy between state 2 and 0, or the same thing as state 2 and 1, is going to be 1019.2 kilowatts. And it has to be kilowatts because that is just kilojoules per second. And we want that per second because this is an open system, right? So yeah, this is synonymous with your work reversible, right? So your work reversible is that just 1019.2 kilowatts. So let's just box that in as our answer. So we got 1 out of the 3. So now we have to find our work actual. How are we going to do that? Well, if you note at the original problem, you're given your second law of efficiency. Isn't that handy? So let's just do the work down here. So if you know that 0.7 equals the efficiency, the second law of efficiency, since this is a work consuming device, your reversible is going to be on top. So it'll be work reversible over work actual. And you can think about this logically because you want a number below 1 to come in here. So your work reversible is going to be smaller because you want, ideally, in the ideal situation, you want the smallest amount of work possible to make this work. All right, so in the ideal situation, you'll have the small reversible, but in the real world, you'll have a big work going, or a bigger work going, to produce whatever results you want. So your work reversible we just found was 1019.2, and then we don't know the work actual, but this is just a simple one variable equation. So divide your work reversible by 0.7, and the work actual is going to come out to 1456 kilowatts. Easy money. So now we took care of 2 out of the 3 questions. So now things are gonna get a little tricky because we want to find the mass flow rate of the water. So we're gonna have to use the equations we were given here. So let me erase some of this. And to find the mass flow rate, you're gonna have to recall that Q equals M cap, all right? Q equals M cap. Let me write that down. So Q equals M being the mass flow rate of the water, which is what we want to find, times Cp delta T, which is the difference in temperature, so we have T2 minus T1. This is an equation you're going to have to realize that you're going to have to recognize to use in this type of problem. So we already found our temperatures, we already know them. And we can find our Cp value of water, which is, by the way, it's not going to be the same as your air. This is for water. So the universal one is 4.18, okay? That's really important for you to know. And we already know the temperatures, so we're trying to find the mass flow rate of the water, but how can we find the temperature? Well, energy balance, my friends. We can just do energy balance. And the energy balance for here, I'm gonna write out the whole thing. So it's gonna be whatever goes in is gonna be equal to whatever comes out in this situation. So it'll be work in plus Q in plus M dot, and since we're neglecting potential energy, we'll just have enthalpy and kinetic energy. So H plus V1 squared over 2 equals work out plus Q out plus M dot H2 plus V2 squared. And this is out, and this is in. So now we have the whole base equation written out, we can start canceling terms out. This is the compressor. We're not going to be producing any work, so this goes away. We don't have any heat going into the system, so this goes away. So we're just left with the work in, and then the difference in the energies. Okay. So when you simplify this, this is going to become 1456 plus 5.35, because we're still dealing with the air. We're trying to find the heat of the compressor. So 5.35 times 1 point. So the H here is going to become CPT. And we know our CP values for air and the temperature that it's at, so that'll be easy. Times 60 plus and you're still going to have to convert it into kilowatts here, so we divide by 2,000. But we're not going to bother here because it's just 0, so it doesn't matter. So once we crunch all these numbers, you're going to get your Q out. And all I did here was skip a step, so I moved this to the left side and have everything equal to Q. So the Q out for this system is going to be equal to 1223.81 kilowatts. So we just found our heat going out of the system using energy balance. So now this value is going to go here, and we're just going to be left with one variable. So let's do this last step here. You're going to see that your M dot is going to be equal to 1223.81, which is your heat, all over the CP value for water, times, and look at the temperature. Do not be confused. The temperature that you're going to use for that change there is not going to be for the air. So it's going to be for the water, which was given in the initial. And they give it to you in the change, so you just have to plug in 10 here. So once you crunch these numbers, the mass flow rate of the water is going to be equal to 29.3 kilograms per second. Final answer. That's it. That's all there is to this problem. We just found the mass flow rate of the water, so yeah, that's all we got for now. Tune in next time.